Good afternoon. Welcome to Krishna's class. Let us continue with our journey from R2, R3 to L2. So what we have done last time was to introduce or explore for an expression of the angle between two vectors. And recall that we had this relation: if x belongs to R2 or R3, y belongs to R2 or R3, we have this is in the case of 2, and this is in the case of y3 determines the angle between the vectors xy in the following way. That is cos theta equal to this is the relationship that we did, where theta is the angle between two vectors. X, this is y, this is the angle between x and y, then cos theta is given by this expression. And it involves this very nice bilinear form involving x and y. Okay, that's the beauty. So there is something inherently in it. Now we will try to explore this. Okay, what are the properties of this? Because if you want to generalize this beyond R2 or R3, where you have a geometric perception of this, you need to know what exactly is this. First of all, you observe that x, y is a real number. This belongs to R, belonging to or R2 or R3. I mean, when I put bracket here, it means in R2 or R3. So it's a map from what you call, say, it is a map from RK cross RK to that is for k equal to 1. So this is the map. There are two arguments for it. So this maps mapping from R to RK, R. So xy gets mapped. 1, 2. So this is the place where we already know the geometry. That's why I am just sticking to A equal to 1, 2. What further properties are there? We have observed that is greater than 3. So that gives what is called the square of the norm. Okay. Then we observe that that is easy to see. Okay. Then we have x, y is equal to, that is, it is symmetric. Then alpha x plus beta y z equal to alpha xy xz plus beta. It is also x this is for x. These are the properties. So it is a bilinear functional on which is symmetric positive or negative. Non-negative in the sense so these are the basic properties that we just got. So that gives some insight into the expression that we have identified to represent the angle between the two vectors. Now that's very interesting. The norm or the length of the vector is also related to the so-called inner product. Okay? So you can derive the length from the inner product in the sense that this is the relation. Okay. Now suppose we want to generalize this. Let us start working on the generalization. Okay. Now this is something which you should because you're all going to be creative mathematicians, or at least some of you are going to be creative mathematicians. and would explore some examples from which you could get worthwhile theory coming out and how these things come out. Let us look at this. The first thing that we observe is this, that you can work out spaces like Rk. So from R2, R3 to Rk, where you don't have any geometric insight to work on, except the algebraic structures that we have observed in R2 and R3, simply carried over to Rk. Okay. So we have take Rk. So let is an N tube, an ordered N tube. Okay. Now we can define x plus y. This is definition. Okay, this is definition which is formed in terms of R2 and R3 that we are familiar. This is equal to okay. And then you have alpha x defined as that is each component you multiply by alpha and then create the vector. So you see that you have addition and multiplication defined on R. Okay. This defines what is called the addition and multiplication. Now this gives the linear space structure. Exactly as in and one can generalize all the results related to this. Can show that Rk over R is a k-dimensional vector space. In the sense that any basis you choose for Rk will consist of exactly k number of vectors. Of course, the choice of basis is not unique, but the number of elements in every basis is the same, which is k, and this is what you call the dimension of the space. So it's a k-dimensional space. Now on this, we can define both addition, both norm and inner product. So we define, first we define so norm is, so we define this as norm of x defined as sigma xi square. Okay. Therefore, with some effort, you can show that this is equal to. We shall see the general case and then the proof will be here. But in this case, you can specifically work it out. You can show that following 1. You can only x. 2. Norm of alpha x this includes both positive, negative. Third property is this is the triangular inequality. So we have successfully obtained norm exactly as in the case of R2 and R3 in RK. But all these things very specific proof, which I am not going to do, but I will do it in general. Okay. Now, thus that means defining the length of a. Now we take up the inner product. Now we come to in this case we define we are just mimicking, doing nothing else. So this is the definition of this we call now the problem is in RK you cannot actually visualize what is the angle between two vectors. But if you want, you can define angle between two vectors by defining this property. So that we will come to that. But you see that this is properties. Whole square is the length. Equal to 0. These are all obvious things that you can easily verify. yx. It is symmetric. It is symmetric. Then and using this one can derive phi, or I'll call it 4 prime, which is derivable using this. For every x, y, z, but this is a consequence of application of 3, so you don't have to state it as it is, but we just make this observation. Okay, so you see that we can straight away generalize from R2 to R3. Our experience on R2 and R3 can be now carried over to a hypothetical space Rk. Okay, and this is, for that matter, it's a finite dimensional vector space. Now, what we do is, this is a finite dimensional, k-dimensional vector space over R. Now, you see that it is equally well possible to consider the associated field as C. Okay, right? It is equally well possible to consider the associated vector associated field as C. The what you call the field of complex numbers. Okay. So we now go further, one more step. Observe that C is a over C, which is one dimension. Is one dimension. For instance, just this is a basis for C over C. So it is a single element at the basis, therefore you call it one dimension. Okay. Every element of C is a scalar multiple or a multiple of this of 1 by a complex number. So everything in C can be generated using 1 with the help of C. And of course, what are the addition and multiplication? You have Z1 plus Z2 is well defined. This is again, sorry, this is again a complex number. So this belongs to C. So scalar multiplication is alpha times defined as I times alpha 1 y1 write it this way. Or I'll write it this way. Alpha 1 x1 minus alpha 2 x2 plus I times alpha 1 x2 y1. So we define as the product. And you see that with now we have the complex plane. Now suppose Z is a vector. Suppose this is Z. Okay. The x y. This is the real axis. This is the imaginary axis. So Z is equal to x plus y. That is the number. What about the length of this vector? So mod Z is the length of the vector. This is actually equal to square plus this is the length. Using again Pythagoras. Okay, it's the length of mod Z. And inner product. How do you define it? Okay, let us do it exactly as we did in the case of real and see what we end up with. Okay, so you get right. So this is equal to. I mean, I am just doing it, trying to do something, but which may not work. So this is actually Z1, Z2. This is questionable. Now, okay, this is my definition. Okay. Now, where does it ask for a modification? This is something which we should realize. It is immaterial whether you define the product, inner product in this way or some other way. This is a linear space anyway. Its length is actually given by this. Now, you see that Z1 belongs to C, Z2 belongs to C, and Z1, Z2 C. But this may not be Vn. So one cannot relate it to the length of by defining put a question mark here. Something which we would like to have. Simply Z square. So Z square may not be not V. So in a way, I think we are stuck. So we have to explore now. So let us now modify the definition of the dot product. What we do is define equal to conjugate. Then ZZ becomes simply this is real. Okay. So instead of this definition, we choose this as the definition. Okay? So that is the first departure when you go to complex case. Addition, multiplication, everything goes in the same way, but this would be different. Okay, right. Now let me work on this. Then you see that is greater than or equal to 0. Okay. And Z is the 0 element. Okay. Therefore, this we choose as the definition. And therefore, let us see now, let us go back into the basic properties of the inner product. And already there is a modification that is available. But this is not alarming. We are not completely departing from the main track that we have followed. We will see soon. And these are the important things that you have to look at. Sometimes a straightforward generalization may not work. Therefore, you may have to rethink about the whole thing, rework the whole thing. But when you rework, the original case that we have considered, if it turns out to be a part of this, then the old definition should agree with the new definition. This is important. So I'll just explain what it is. Okay. Now you see that these are the properties. These are complex numbers. This is a complex number. 2. So that we have checked. Now the third one that you have to see is the following. What about the symmetry? Is that going to work? Is this equal to Z1? Obviously not, because this is going to be Z1 conjugate. This is going to be Z2 Z1 conjugate. This may not be equal. In general, they are not. So what do we have to do? To see that from these two are equal, provided you take the complex conjugate of this. Therefore, we replace 3. We take as conjugate. Okay. So there are some departures already. Okay. Z1, Z2 is not equal to Z2, Z1, but it's a conjugate of Z2, Z1 by our definition. Okay. Right. And that is because he wanted to have this non-negative. Then of course you had the following properties. This is easily verified. Okay, but this is not symmetry. This is what you call conjugate symmetry. Or what you call, later we will introduce that terminology. And 4 prime, this can be obtained by using 3. These are complex numbers. This is equal to alpha 2 conjugate Z1 Z3. So you see that the coefficients come out with a conjugation once they are in the second position. Okay, so that is the consequence of this conjugation that is appearing 3. Okay, so there are already some non-trivial modifications that we are working. So the desirable properties of the inner product in the complex case are defined. But is it a generalization of, is it a worthwhile of the real case? Then only there is unification. Otherwise, the two things are going to be totally different. Okay. Okay, let us explore this. See that any real number is a complex number. With imaginary part that is Z real if and only if X plus I0. Okay. Now you see that with this identification, you see that suppose Z1 and Z2 are real. Then equal to, we are just applying this definition. Conjugate. Now this is the same as Z1. Why? Because this is equal to conjugate by definition, and that is equal to Z2 Z1. Okay. Therefore, you see that when Z1 and Z2 are real, this is derivable from the new generalized form. That's interesting. So let us generalize this. Consider Cn. Now Cn consists of Z, Zn, each Zi, then you have okay. This is equal to, so it is defined. So also alpha Z is defined as Zk. That's the definition where alpha belongs to C. This is how it is defined. Okay. This is a direct generalization of this, because you see that Ck becomes Rk provided every one of these complex number is a real number, because every real number is a complex number. Okay, so every real number is a complex number, and therefore Rk is goes inside that. Rk over R is whatever is happening can get. Okay, right. Now let us, then Ck is a k dimension It's a k-dimensional vector space over C. Now you define and this is of course greater than or equal to 0. This has all the nice properties of the length, right? So also you define or C. So that's a generalization. And you see that when the Z is an element of Rk and W is an element of Rk, then you see that this conjugation won't be there. So you get back the original definition. And from this, you will immediately see that this is true. Okay. So you have seen the generalization has to be very carefully done. Okay. That's something which one has to be careful about. One should very carefully go through the process. Okay. So now we have traveled a lot. Okay, from the real space to complex space. Okay. Now you see that in general, if you take a field, then Fn over F is a vector space. But you can't go beyond that, cannot define a length because F may not be containing real numbers. Okay, and you cannot define an inner product because the F may not be containing complex numbers, because they are specifically maps not just to the fields, but then you see that the concept of length, the concept of angle between the vectors is coming into the picture here. Okay, so we are not interested in working out Fn over F. We are interested in working over any vector space defined over C or R, or any subfields of C. Okay, so that is the status that you have. Okay, now we have, with all these things, we can now abstractly define what an inner product space is. So the abstract definition of the inner product space is what we are seeing. I think I conclude here today, and maybe I'll come up with a continuation of this in my next lecture tomorrow. Thank you very much.